Hello, everyone. It is our great pleasure to have Peter Winkler as our today's speaker. He will talk on the shape of large permutations. As always, we will record this talk. It will be available on YouTube after a few days. If you have questions during the talk, you can write in the chat. We'll try to raise them to Peter. And of course, at the end, we'll have time for questions. And then we'll also have some time for informative discussion after, which will not be recorded. So Peter, the floor is yours.
Thank you, Liana and Hansa. This has been a delightful series of seminars, I have to say, and I'm very pleased to be invited to be part of it. I'd like to talk about large permutations and work that began at ICERM at Brown University with Rick Kenyon, Kráľ and Charles Radin. And some is continuing with the current research group that I'm part of, which consists of Sumit Mukherjee, who's a former student of Percy Diaconis's, and his student Sayan Das, and Rick Kenyon's former student Martin Tassy, and my former student Chris Coscia. Okay, so this little picture shows you where I see myself sitting in the world with interests in combinatorics and probability and the theory of computing and statistical physics. And in these fields, a common observation, something that's often been made in the seminar series certainly, is that large random objects tend to look alike, right? I mean, we almost take this for granted now. A random object could be anything. But when we take large random objects with many small parts that interact, they tend to look alike. And a natural question to ask is, of course, what in fact do they look like? And a common approach is, well, count things, take limits, try to figure out as n goes to infinity, what shape things take. Okay, so today, I want to talk about permutations. Now, permutations, as you all know, show up everywhere in mathematics. And they can be thought of in a number of different ways. You could think of them as members of a group with their algebraic properties. You could think of them as bijections from some unordered set to itself. But for our purposes, we'll think of them as simply reorderings of the numbers from 1 to n. And as such, you might think, okay, what kind of statistical properties do we care about for a large permutation? Those of you who've dealt with graphons know that one way of dealing with, useful way to deal with large graphs is to think about what happens if you look at a random set of vertices and what subgraph do they induce. And the equivalent for permutations is something called patterns and pattern densities. So a pattern is itself just some small permutation, like 1, 3, 2. And that just represents the permutation that takes 1 to 1, 2 to 3, and 3 to 2. And if we have an example large permutation, in this case 6, 2, 1, 4, 5, 3, 7, then an occurrence of the pattern in the permutation is just 3 places in the permutation where the relative ordering is the same as it is in the pattern. So in this case, it would be 3 numbers where the first one is the lowest, the middle one is the highest, and the third one is between them. So for example, 2, 4, 3 would represent an occurrence of the pattern 1, 3, 2. So would 253, 143, 153. I think that's all of them. And the pattern density is the total number of occurrences of the pattern in the permutation divided by the number of places to look for the pattern, which is just n choose k. Right? If the pattern is of length k and the permutation is of length n. In this particular case, there are 7 choose 3 ways to pick out a pattern, and 4 of those, if our counting is right, give you the pattern 132. That gives you the pattern density 4/35 for the pattern 132 in that permutation. Okay, so all right. So now we introduce a limit object for permutation, and this is quite, I think, surprising, and in some respects more nicely behaved than you possibly imagined thing. It's just a probability measure on the unit square with uniform marginals. But in particular, a Borel probability measure, and you could just call it a doubly stochastic measure, and statisticians might know it as a 2-dimensional copula. And these things are exactly the completion of the class of all permutations of all sizes under a certain metric, which I'll describe. Okay, so let me first tell you what permuton corresponds to a given permutation. If we take the permutation 15324, we could think of it as a matrix. Now, I'm going to use the analyst's point of view rather than the algebraist's point of view. So the analyst starts in the lower left corner and thinks of the x-axis along the bottom and the y-axis going up the top. So we read this as 1, 5, 3, 2, 4. And if we want to turn this into a permuton, we just make the probability measure, which is concentrated on the squares where we see 1s in the matrix, and is empty where we see 0s in the matrix. So each of these squares is just a little flat top building of density 5, so that the measure of the whole thing is 1. And so that permuton is permuton gamma. That strange Y-looking thing is a gamma in my font for some reason. Maybe it stands for Eupremian. And so gamma of 15324 is this permuton. Okay, so every permutation gives us a corresponding permuton. Okay, so suppose we take a uniformly random permutation of length 1,000, and its corresponding permuton would look like this. I'm not even sure you can see that there are 1,000 tiny dots in this picture. Each one represents a very tall, narrow building of height 1,000. That might look very different from the uniform probability measure, which I've indicated on the right by just coloring the square uniformly gray. But actually, for our purposes, these are almost the same. So we'll say that a sequence of permutations converges if their permutons converge in distribution. In other words, their cumulative probability distributions converge pointwise. So what that means is if we take some area of the picture on the left and we take the same area cut out of the picture on the right, we'll get about the same probability measure, and that will be. Literally, the CDF of gamma is just the probability that you, at a random point, falls in a lower left rectangle, which is x. Okay. Now, if we're given a permuton, so permuton, again, it's a probability measure with uniform marginals on the unit square. You could think of it as the joint probability measure of two uniform random variables on the unit interval. And you can pick points out of it, and you can use those points to make a random permutation. Pick n points from the permuton gamma, sort them by x coordinate, and record the permutation that the y coordinates give you. For example, imagine this is a permuton. We pick those 3 points from it. And so what permutation would that give us? We look at the y coordinates. We read the x coordinates from left to right. And the y coordinates are middle, top, bottom. So that's the permutation 2, 3, 1. So we now have a way to go from permutations to permutons, and from permutons back to random permutations. Okay, so the density of a pattern I of length k and a permuton, well, to get the pattern density for permuton, you would take some huge permutation generated by this permuton and then count the patterns in it. But you don't have to do that. It's the nature of a permuton is that if you want to find a pattern density for it, and the pattern is the length k, you just need to pick the k points and see how they fall, and that's your pattern density. And that can be computed as an integral. This would be the integral you would get if you wanted to compute the 2-1 density, which is sometimes known as the inversion density of a permuton. So how often does it reverse the order? So it's not quite true that the pattern density of a permutation is the same as the pattern density of its permuton. Well, it's true as the permutation gets large. But the pattern densities and the permutons work together beautifully. So this theorem tells the following and more. First, this is not obvious, but a permuton is determined by its pattern densities. So if you know the density for every possible pattern, that gives you the permuton. You know, that fact continues to surprise me because there are not that many sequences of pattern densities. And it seems as if there are an awful lot of probability measures on the unit square. But every probability measure with uniform marginals on the unit square determines a different set of pattern densities and vice versa. And as I mentioned before, permutons are exactly the completion of permutations in this pattern density topology. So if you want to make a metric out of the pattern densities, you can just say that to measure the distance between two permutations, you first look at its 1, 2, and 2, 1 densities, and it's just that they're close. And then you look at the densities of length 3 and ask, okay, are they close, and so forth. And you can weight these things by the inverse powers of 2 or something. So permutons have, in effect, the same relationship to permutations that the real numbers have to the rational numbers, and that graphons have to graphs. Here are a couple of examples of permutons that show up in nature, you might say. Suppose you take n-1 steps of a random walk on the real line and pick any symmetric continuous step distribution. It doesn't matter what the distribution is. Then as you step back and forth on the real line, you're creating a permutation of length n, and you can ask, as n gets large, what does that permutation look like? And in fact, it looks like that, regardless of what the step distribution is. So in this picture, the axes actually extend up to infinity, but they were necessarily cut off so you could see what's going on. The reason why, so it looks from this picture as if we're giving a lot of extra weight to the identity permutation, which runs from 0, 0 to 1, 1, and the reverse identity, which goes from 1, 0 to 0, 1. And that's true. If you think about it, if you take a random walk of n-1 steps, then the probability that you go up every time in the symmetric random walk is 2 to the minus n, which is much more than 1 over n factorial. So the identity and reverse identity permutation are being given more weight, and this permuton reflects that. There's an actual formula for it, which looks like this. Here's another wonderful case. Stages of a random sorting network. Right? So take a, on the left, you see the identity permutation 1, 2, 3, 4. And suppose you want to flip it. And there are, that takes n choose 2 steps if you do it efficiently. And if you do it efficiently, uniformly at random, you can ask about what do the permutations look like that you encounter en route. And in fact, they look like these permutons. The one in the middle is it's a beautiful thing. It's just, it's the projection of the uniform probability distribution on a sphere, of a sphere projected onto the unit square. There's a couple of notches in this thing. Those are artifacts. Ignore them. Okay, so what do we do now? Okay, so we want to use these permutons to study classes of permutations, in particular subsets of the symmetric group. And we are going to use them to study subsets that are large, okay? So of course, the largest subset of Sn is the whole thing, which has size n factorial. And in general, what we call a large subset is something that is within exponential reach of n factorial. In other words, it's equal to n factorial e to the Cn for some non-positive constant c. Okay, which we could think of as e to the n log n minus n, which is n factorial plus Cn. Okay, again, c is some, think of it as negative number. And we're going to use that number c to measure the size of these sets and to figure out which ones are dominant. So examples of such sets are permutations with certain fixed pattern densities. So we could say, look at the set of all permutations whose 2-1 density is equal to a third. Okay. If we look at permutations, one of whose pattern densities is 0, then we know from the famous proof of Marcus and Tardosh, the Stanley-Wolf conjecture, that these classes are only exponential in size. So these are too small for us at the moment, but later on at the end of the talk, I'll get back to talking about sets of that size. Okay, so it makes sense. We have a permuton gamma. We know that by picking endpoints from it, we get a random permutation in Sn. We can ask for the entropy of this probability distribution. That would be a measure of how much weight, in effect, to give to this permuton. And the entropy is just the ordinary Shannon entropy, which if for probability distribution, just summation minus p log p. We'll see this formula on Shannon's tube. So the uniform distribution on Sn would have entropy the log of n factorial. And the entropy of a permuton is just then defined as take the entropy of this distribution, knock off log n factorial, divide by n, take the limit as n goes to infinity, and by doing that, basically we've isolated that non-positive number c that we were talking about on the previous slide. Okay. The theorem is that you can get that value by just integrating g log g, where g is the probability density for the permuton. Of course, that probability distribution, I mean, lots of probability distributions don't have densities. And if that's the case, the claim is that the entropy will be minus infinity. And that actually it can be minus infinity even if g log g, even if g does exist, but g log g is not integrable. So this means that somebody gives you a permuton, do this integral, and you know basically how many permutations that permuton represents. Here's some sample entropies. Well, if we take a permuton which is singular, a singular measure, then it has no probability density, and its entropy is minus infinity. So this is the permuton that corresponds to the identity permutation. The uniform probability measure is the only one whose entropy is all the way up to 0. The entropy of the permuton of a permutation of length n is minus log n. The permuton is entropy is never positive, it's only 0 for the uniform measure. Okay. So now, in order to use these guys to try to determine the shape of large permutations, we need a large deviations principle. And various versions of which were given by Trashras back in 2008 by Sumit Mukherjee, my current collaborator, and by the group of us in 2015. And such a principle looks something like this. You have a nice set of permutons. What does that mean? Could be closed or open or even both in the permuton topology. And, and what this says is that to figure out the size of the set of permutations these represent, you just want to find the permuton in your set with the biggest entropy, and that entropy will give you the answer. So maximize the entropy to find out what the bulk of these things look like. So basically, in words, the variational principle says, if you want to describe and count permutations with given properties, for example, fixed pattern densities, you find the permuton that has those properties and that maximizes entropy. Of course, easier said than done. But we'll see some cases where we can actually do this, and lots of cases where we can do it basically experimentally. Okay. So an example, well, the simplest pattern is the pattern 1, 2, or the pattern 2, 1, patterns of length 2. And okay, so there are lots of permutons with any given density row, but there'll be one of them, a unique one in this case, that has maximum entropy. And we actually knew already what that maximum entropy was and what the permutons looked like. And I'll show you. But the conclusion is that if you take a uniformly random permutation with some particular density of the pattern 1, 2, then we know what it will look like for large n. So this is in fact how they come out. Well, if the 1, 2 density is 1, the permutation can only be the identity. So that's not too interesting. But if it's 0.08, it looks like this picture. So it's heavily weighted toward the identity. It's curled up a bit at the ends. If you think about it, it has to be in order to have uniform margins. So it looks a little bit like a Viking ship, maybe. As it gets near a half, it smooths out. Here it's below a half, so it's actually higher at the reverse identity position. At 0.02, it's of course just rotated 90 degrees from the 0.08. At 0, it's the reverse identity. And so Shannon Starr already in 2009 computed, these are our computations, which are stated in a somewhat different way, but they're the same. The actual probability density for this thing and the corresponding entropy curve. So this is typical of what you get if you pick a pattern. Its entropy will be minus infinity at density 0. It'll go up to 0 at 1 over k factorial, which is the probability of finding the pattern in a uniformly random permutation. In this case, just 1/2. And then back down to minus infinity at the top. Okay, so our proof of this large deviation principle is basically from scratch and uses a lot of analysis. But I wanted to mention one very nice combinatorial lemma which comes up in our proof. And that is Baragnai's lemma, which says that if you have a real matrix with integer row and column sums, then you can round each entry up or down in such a way that both the row and the column sums are preserved. So here's not a very elaborate example. I just used 1 decimal place, but here's a real matrix whose row and column sums happen to be integers. And the lemma says that we can round each guy either up or down and get an integer matrix with the same row sums and the same column sum. And why is that useful? Well, yeah, if you're given a permuton, you want to prove this variational principle. You want to generate a lot of permutations that you might get by picking points from this permuton. But of course, the logical thing is to divide the permuton into a grid, but the permuton's values in the grid squares will not be integers. So in order to pick a permutation, you want to pick integers that are close by, but they still have to respect the and add up to the right numbers for the rows and columns. That was a fun piece. Okay, so here I'm just going to run quickly through a couple of things that we were able to do rigorously. So in the cases where the entropy function actually is a convex function, then you can reasonably actually solve these equations and find out what the highest entropy permuton is. So here's an example here where we're simultaneously looking at the 1,2 density and what we call the 1 star star density, which is the 1, 2, 3 density plus the 1, 3, 2 density. That's the density of triples where the first guy is the lowest, and we don't care what order the second and third guys are in. And this is a feasible region for permutons with respect to the 1, 2 density versus 1 star star density. And these are what some of the permutons look like that correspond to various points in the feasible region. Along the boundary of the region, the corresponding permutons are singular permutons with entropy minus infinity, and they're indicated with these pictures. Okay, and this is what, oh, that's right, this is concave, look at from underneath. And that's why this case is solvable. That's what the entropy function looks like, looking up from underneath the feasibility region. Okay, yeah, just a few words about how this technique works. You're doing this variational problem where you want to, basically doing calculus of variations. You can use Lagrange multipliers, and you end up with a partial differential equation, a form that looks something like this. And basically, the idea is very simple. You have a permuton. You pick a little square inside it. And what you can do is you can add a little bit of mass to 2 diagonal subsquares and subtract a little bit of mass from the other 2 and preserve the uniform marginals for this probability distribution. And if you can do that and increase the entropy, then you have to do it. So the PDE just says that this has been done to the extent possible. And doing this either rigorously with calculus or empirically with computing help can get you to permutons, winning permutons, I call it. Now, there's a curious contrast here, which I want to talk a little bit more about. So when you do this, you get a beautiful analytic function as the probability density for your permuton. When you do it rigorously, you always get such a thing. When you do it empirically, you always seem to get such a thing. But when you do the same thing for graphons, okay, so for graphons, there's also a variational principle, in this case proved by Chatterjee and Varadhan. And it has a different entropy function for graphons, but that's okay, it works quite similarly. But when you maximize them, you don't get these smooth analytic things. Instead, you get sort of combinatorial things. You get what Radin and Sadoun call multipodal graphs. Graphs divided into a finite, the vertices are divided into a finite number of bunches. And in each bunch, there's a certain random allocation of edges with a certain probability inside the bunch and with certain probability connecting other bunches. Okay, so here's an example of that. So this is a famous picture, which we call the scalloped triangle. And it represents the feasibility region for graphs, actually literally for graphons, or if you want the closure of the feasibility region for graphs, where the x-axis represents the edge density of a graph, and the y-axis represents the triangle density of a graph. Okay. So for example, the lower left corner here has edge density 0, therefore it's the empty graph. The upper right-hand corner represents the complete graph. The lower right corner is a graph with edge density 1/2 and no triangles. So that has to be the balanced complete bipartite graph. This point represents the balanced complete tripartite graph, and so forth up the line. And these boundary lines between them are slightly concave. So, this is a beautiful and difficult piece of work by Asparov. But here's the fun part. We can change the graphs to permutations. We can change the edge density to 1,2 density. We can change the triangle density to 1,2,3 density. And we have exactly the same picture. So why is that? Let me just give you an indication. To get from permutations to graphs, we could take a permutation. So think of that permutation as an ordering of the numbers from 1 to n. We can intersect that ordering with the standard ordering of the numbers from 1 to n, right? So that gives us a partial order where I is less than j if I is smaller number than j, and also I comes before j in the permutation ordering. And then we can look at the comparability graph of that poset, and that gives us a graph. And so let's give an example. So more specifically, permutation pi intersected with the standard ordering gives us a graph with I less than j if it's less than in numbers and pi is less than pi j. And here's an example from before we take the permutation 1, 4, 2, 3, 5. If we intersect that with the standard ordering of the numbers, we get this poset. And if we take the comparability graph of that poset, in other words, we connect two numbers if they're comparable one way or the other, then we get this graph. And the claim is that occurrences of the pattern 1, 2, right? So just an increasing pair in the permutation correspond to edges. So here's the increasing, here's the jump from 1 to 4. That's this edge of the poset, and it's this edge of the comparability graph. 2, 3, 5 is an occurrence of the pattern 1, 2, 3. That becomes a transitive pair of edges of the partial order, which becomes a triangle in the okay. So what does that mean? So we can go from permutons to graphs, get this correspondence between patterns and subgraphs. And that means that the feasibility region for permutations is contained in the feasibility region for graphs. But it seems surprising that since relatively few graphs are comparability graphs of anything, let alone comparability graphs of two-dimensional partial orders, it seems surprising that it fills out the whole feasibility region. But it's actually easy to prove. This is a singular permuton that depends on two parameters, A and B. We're going to pick B, so it's always at most a half of 1 minus a. So we get an A piece coming down from the top here, and then at least 2 B pieces and maybe some fraction of a B piece left over. So that defines a class of permutons, and we want to make sure it includes the case B equals 0, which would turn this bottom part into just an increasing line like this. So this definition in the permuton topology represents a continuous set of permutons parameterized by A and B. And the cool part is that with these guys, you can cover the whole boundary of the scallop triangle. So for example, the lower left corner of the scallop triangle, that just corresponds to A equals 1. So that's the reverse permutation, which has no 1, 2 patterns. And the complete bipartite graph is represented by the A part is 0, and there's just a B line here and a B line here. That gives you the complete balanced bipartite graph. So you cover the whole boundary, and now by topology, we extend this space extends to the entire simply connected region between the boundaries. All right, and if we actually do that, now here we have pictures of lots of the permutons that actually show up inside this feasibility region. And these were all generated by computers, so these are not rigorous. But you can be pretty sure, I think, that this is what. Okay, so here is another case where the graph feasibility region is the same for permutations. Here, instead of triangle edges versus triangles, it's triangle density versus anti-triangle density. Right? So we pick 3 points, vertices at random out of the graph or graphon. And the x-axis tells you the probability that you get a triangle there. And the y-axis tells you the probability that instead you find no edges at all among connecting those 3 points. And of course, these 2 parameters are related in that they cannot sum to more than 1. And the actual feasibility region is a kind of a funny region. That the upper boundary of this region is consists of 2 curves that cross in the middle. So it's the top half of one of the 2 curves and the bottom half of the other curve. And so what's going on here is that if you look at the permutons associated with the boundary points, well, first of all, let's go to permutation. So now we're talking about 1, 2, 3 density versus 3, 2, 1 density. And the singular permutons that correspond to boundary points are indicated on this picture. And at this key point in the middle, there are 2 competing permutons. Okay. Now, these 2 permutons are actually singular permutons. They have entry minus infinity. So the variational principle is of no use here. But we did manage to prove that this conflict extends inside for some portion toward the origin. So along this line, there continues to be a pair of permutons, this time with finite entropy, that compete for being the maximum entropy permuton. So there's a genuine phase transition along some line that goes in here for some distance. Okay, this is the first phase transition that we were able to identify rigorously. But let me just mention that going back to the graphon case, Radin and Sadoun were able to show that there are many phase transition boundaries inside the topography of the scallop triangle for graphs. Places where you suddenly change from graphs with 3 different interesting regions to graphs with only 2, or you flop from all kinds of interesting things happen. We don't know much about what happens inside the scallop triangle for permutations. Okay. So let me conclude with some remarks about those singular permutons. So the singular permutons are of particular interest to people in a lively community of combinatorialists who study permutation patterns. And this work was motivated by the original work of Herb Wilf and Richard Stanley and others, and it's mostly motivated by studying permutations that avoid particular patterns. And those are only exponential size, so they have singular permutons. And this whole mechanism that I described to you is as useless for them as graphons are for studying sparse graphs. You need another concept, which is probably not going to work as well. So here's examples of singular permutons. These arise in various cases. The one on the upper right here is a permuton that maximizes incidence of the pattern 132. Quite interesting. There's more of these lines that head down toward the origin. And okay, so again, each of these induces a probability distribution on Sn. But now the sizes of the entropies of these probability distributions will not be enough to give us finite entropy. But we can measure the exponential growth rate for these things instead. And so we use what we call catropy. The prefix cata, as in catacomb, means like the basement, down underneath. So this is kind of a low-level basement version of the entropy that we talked about before. And for this, we just compute the limit of the entropy of the probability distribution divided by n without subtracting off that log n factorial. So this, thankfully, will be non-negative things instead of non-positive things. It could be infinite even for a singular permuton, but it's usually finite. And it corresponds to exponential growth rate of something called geometric grid classes that come up in the work of David Bevan and Michael Albert and Vince Vader and others. We have lots of conjectures and relatively few actual results, but we're working on it for theorems about catropy and about the behavior of these singular permutons. So that is all I have to say today, and I thank you very much for your attention.
Thank you, Peter. So please unmute yourself. Let's give a round of applause to Peter first.
Thank you.
So questions?
So maybe I have actually, we talked relatively recently about, maybe similar set of problems, even though you may have solutions now with Mateusz, who is maybe here. So could you say a little bit about, connection you have, that you either believe or you were able to establish between, I don't know, limits of permutations that avoid, say, randomly chosen permutations that avoid a certain pattern. So is there a conjecture, say, about the restriction of these measures? Of course, they can't have an absolutely continuous part, but can you say more?
I don't think we can add anything to what's known about at the moment, to what's known about classes of permutations that avoid a pattern. You might think that by computing the winning permutons using our variational principle for interior points of a feasibility region, and then walking toward the boundary where the where the pattern density is 0, and watching what happens to these permutons, that we would find sitting there the singular permuton that represents that class. But in fact, several problems interfere with that. One problem is that if you walk to the boundary point from different directions, you might get a different singular permuton. That's pretty disconcerting, but it can happen. And secondly, we know that in fact, there may be many singular permutons that represent a single pattern avoiding class. So there's some marvelous work by, I won't try to mention the names of the authors, but there's marvelous recent work about a case of if you avoid certain patterns, you get a class of what are called separable permutations. And if you take limits of these, you end up with random permutons, random singular permutons that they call Brownian permutons. Fascinating objects. Jacobo Borga, who maybe is here, knows a lot more about these than I do. Okay, we do have some conjectures about what happens at the other end. That is, instead of minimizing the density of a pattern, you try to maximize the density of a pattern. Then we think that it might well be the case that you get down to a unique permuton. But we're pretty far from being able to prove that. We can't even prove much weaker statements than that yet.
Thanks. Any more questions?
Yeah, yes, if I could. I just wanted to compare permutons with the graph world in which the GNP is kind of, for different values of P, GNP is very similar to itself. It corresponds to the constant per graphon. But in the permutation world, it seems that only for value 1/2 it is a simple object, but for other values it is pretty weird. And
that's a great, yeah. Let me show you what's going on here. I can get back to my slides for a moment. It's a great question. Hang on. Let me see if I can. Oops, darn. That didn't work. Here we go. There. So here again is the scallop triangle. So in this picture, I don't know if I could draw this, but there's a curved line that goes from one end to the other of the scallop triangle. In its interior, somewhat like this, if you can see my cursor arrow. And that curved line represents GNP. And those Erdős-Rényi graphs are very high entropy. They're the highest entropy graphs possible with a given edge density. You just take every edge independently at random with that probability of that density. And so that represents, if you've drawn the entropy topography for this picture, that represents a ridge that goes up from the lower left to the upper right. And Radin and Sadun were able to show that that ridge drops gently on one side and precipitously on the other side in entropy. Okay, now if we switch to permutations, we get not just the 50-50 point that you mentioned. Well, actually, it's not 50-50, it's, yeah. The point you're talking about, the uniform has 1,2 density, a half, and 1,2,3 density, 1/6, 1/3 factorial. But in fact, you remember the picture of the winning permutons for different values of 1,2 density that have been gotten by Shannon's star? That takes the place of the Erdős-Rényi graphs here. So for each 1,2 density, there's a maximizing permuton, and that gives us another curve in the interior from the lower left corner to the upper right corner, but it's not in the same place as the Erdős-Rényi curve. And it seems to have different phase transition characteristics as well. So even though the feasibility region for the permutations and the graphs are the same, the topography of this picture, the entropy topography of this picture, is quite different from the graphs to the permutations.
Thank you. Any more questions? Okay, let's give another round of applause to Peter, and then I'll stop recording. Thanks a lot, Peter.